We're charging an inductor and we're looking for the multiple of the time constant for when the energy stored inside is only 0.429 of the maximum. So let's remember the Umax equation is going to be 1/2 inductance times the Imax squared. And for at any point in time during that charging process, you could say that the energy is 1/2 of the inductance times I as a function of time squared. Now we could plug these two things into this equation and we'll get 1/2 I, and then I as a function of time squared equals 0.429, and there's going to be 1/2 I and then I max squared. Let's cancel out the 1/2 i's on both sides, and then let's square root both sides. So we'll get that IT equals the square root of 0.429 times I max. And that's great. Now let's look for the equation of the I as a function of t in the charging inductor. We would use I function of t equal to epsilon over r, and then we could say 1 minus e to the negative t over ti, and we are getting close. We want that stuff. We're going to set that equal to the square root of 0.429 I max, and we're also going to remember that I max is supposed to be epsilon over r. So like, these things will cancel from both sides, and you're going to be left with this equals that. Now let's rearrange this a little bit. I'll put 1 minus the square root of 0.429 on this side, and I'll set that equal to e, and there's the negative t over ti on that side. Now I can basically just take the ln of both sides. So the ln of 1 minus the square root of 0.429, and I'll put a negative sign over here, is going to be equal to t divided by ti. So if we could solve that, then we'll have our answer. We'll do negative ln of 1 minus the square root of 0.429. So we get the answer of 1.06 or so. It's the multiple of the time constant.